Let us solve another numerical problem from engineering mechanics, problem set 2.5, solution to 2.76. Before I proceed, let me remind you certain things which I discussed in previous videos. The reminder is like this. Suppose there are two forces. Let's say this is 5 Newton to this side and there is another 5 Newton to this side. Can the resultant be 0? No. If you shift this vector to this point, then the resultant will be to this side. That will be square of 5 plus square of 5, that is equal to 5 root 2 Newton. So the resultant of two forces like this, one like this and one like this, equal in magnitude, or they will not be 0. So when they will be 0? If there is one 5 Newton to this side and there is exactly opposite another 5 Newton to this side, then the resultant will be 0. Similarly, here these two forces are concurrent. If you extend the lines, they are concurrent here, but they are not here also they are concurrent, but here they are opposite to each other, and therefore the resultant is 0. Similarly, suppose you have three forces, one to this side, let's say 4 Newton, one to this side as 3 Newton, and there is another, let's say, and the resultant of these two, since they are 90 degree apart, square of 4 plus square of 3 and square root of that will come out to be 5 Newton to this side. Now, if there is a third force exactly opposite to this 5 Newton, that is the resultant of 3 Newton and 4 Newton, then this 5 Newton will cancel with this, then the resultant will be 0. So this one and this one, they are concurrent, and the resultant of any two, that is this one in this case, is exactly opposite to this one, and both are equal in magnitude. Therefore the sum of the three forces is 0. But in this case, let's say this is 4 Newton force, this is 3 Newton force. I am taking 90 degree for convenience only. You can have any angle between those two forces. And suppose there is a third force like this. Suppose there is a third force like this. This, say 5 Newton. Can the resultant of this and these three forces be 0? No. Because the resultant of these two will be pointing to this side, which will be 5 Newton. And again the resultant of this 5 Newton and this 5 Newton, if you construct a parallelogram, will be pointing to this side. So, which is not 0. So, the conclusion is for three concurrent forces lying in the same plane, they should have the same point of concurrence, and the resultant of any two must be equal in magnitude and in opposite in direction to the third one for sigma x and sigma y is equal to 0. Now let us go back to the problem. Now the statement of the problem set 2.5 solution to 2.76 goes like this. A weightless bar, AB is a weightless bar, AB is a weightless bar, is supported by a vertical plane. This is the vertical plane from which it is supported, vertical plane by a hinge at A. Here is a hinge at A, one end of the bar, that is the end A is supported here by a hinge, and a tie bar. This is a tie bar. If this tie bar is not there, even if this weightless bar is supported here, due to it will fall down. It will fall down. So it is supported by this tie bar CD. So there will be axial force in the tie bar to this side, let it be S, which is holding the bar AB from falling down like this. And determine graphically the axial force F, S. We have to determine this axial force S developed in the tie bar. induced in the tie bar by the action of a vertical load P applied at B. Now, this axial force, since the bar is weightless, if the bar was having some weight, then due to its own load vertically downward, the tie bar will be under tension. There will be an axial force. But the tie bar does not have any weight. Here is a vertical load applied at point P. So this vertical load will try to rotate this tie bar, will try to rotate this bar AB about the point A, like this. So the tie bar CD will develop an axial force S to this side. So due to this load P, there will be an axial force S developed in the tie bar, since the given bar AB doesn't have any weight. Induced in the tie bar by the action of a vertical load P applied at the end B as shown. Now let me tell you what is a tie bar. These are used for holding faces of rigid slabs in contact and to maintain overall interlocking between the slabs. Also used in plain joints, concrete pavements to connect two lanes. But these are not designed as a load transfer device. Now let us look at the diagram and analyze the various angles and apply sigma x and sigma y is equal to 0. Now if you look at the diagram, this angle is given as 45 degree, here this angle is 90. So the remaining angle, this angle in the triangular shape CDA, which is right angle D, so this angle will also be 45. So given DAC, angle DAC is 45, therefore angle ACD will also be 45. This angle will also be 45, since angle at D is equal to 90 degree. Now let S is equal to the axial force in CD in the tie bar because of the load P, which is trying to make this weightless bar fall down. So the tie bar CD will be developing an axial force away from this point. See, if you consider this point, it is towards this side. If you consider this point, it is towards this side. The same S, we have to find that. So S is acting away from point C. Now, as I have told you before, you have to first find out the point of concurrence of two forces. So if you produce this line of action of the axial force S towards this side, it will meet at this point. Let this point is equal to E. So from this point, S is acting to this side, P is acting to this side. So obviously, therefore, the reaction force developed at A must pass through the same point, and that will be in the direction opposite to the resultant of S and P. Then only the condition of equilibrium will be established. So the line of action of the load P and S meet at point E. Therefore, the conclusion is, therefore, the reaction at A, that is RA, must pass through E. Now, so at this point, the reaction force is not to this side. It will be pointing in the direction of AE. So that is what I have explained here. So this is the point of intersection of the axial force S and the vertical load P. So the reaction developed at A, RA, should pass through the same point, means pointing to this side. If you draw here the x-axis and y-axis, let us this angle be alpha. So this angle will also be alpha, being vertically opposite. This will be your RA. So if you draw this as x-axis, this as y-axis, your P is completely along y-axis, so this will not have an x component. S is completely along x-axis, so this will not have a y component. RA makes some angle with x-axis, let's say alpha, which we will find out. Then RA will have a horizontal component along positive x-axis that will be opposed by S. And from here, if you drop a perpendicular on y-axis, now this length will be RA times sine alpha, that will be opposed by P. So if RA sine alpha is numerically equal to P, sigma y will be 0. And if RA cos alpha is numerically equal to S, then sigma x is equal to 0. So for that we have to first find alpha. So I have redrawn a diagram for you here. This point is same thing as E. From this point your axial force S in the tie bar CD is acting to this side, and from here to here in this direction is your RA. This angle is taken as alpha. Now the question is what is the length of this line from D to E? So you have to go back to the original figure. From D to E will be same thing as this distance, 1.5 plus 1.5, that is equal to 3 meters. So from D to E is equal to 3 meters. So from D to E is equal to 3 meters, and from D to A, how much is from D to A? Or from A to D, what is this distance? This distance will be 1.5 meter. Let me explain. Now here in the original figure, this was given 45. This we calculated as 45 in this triangular shape. So the length of AD is equal to length of CD, and since CD is equal to this distance 1.5, therefore AD is also 1.5. So since DAC is equal to DCA, the angle, therefore AD is equal to CD, that is equal to 1.5 meter. Now let us take tan alpha of this angle will be perpendicular AD over base DE, that is equal to AD over DE. So 1.5 over 1.5 plus 1.5, that is 2 times 1.5, 1.15 cancel. So we are left with 1.1 by 2. So alpha is tan inverse 1 by 2, that is 26.56505 degree. Using a scientific calculator, if you convert it to minutes and seconds of arc, this exactly comes out to be 26 degree 33 minute 54.1 in seconds of arc. So since alpha is found out, this angle is found out, let us draw the free body diagram at point E and resolve RA to horizontal and vertical components. So that is in the next page I have done. So this is your point E, RA to this side, P is vertically downward along negative y-axis, AC is along negative x-axis. So this will have this length as the vertical component RA sin alpha. From a drop a perpendicular, this length will be RA cos alpha. So let us apply sigma y is equal to 0, means to this side is your RA sin alpha. So RA sin alpha will be equal to P in magnitude, and since they are already opposite in direction, so if the magnitudes are equal, they will cancel. So will make sigma y is equal to 0. So sin alpha comes to this side, so RA is equal to P over sin alpha, make it as equation 1. Then apply sigma x is equal to 0. The axial force S developed in the tie bar CD pointing away from C along negative x-axis should be balanced by your RA cos alpha if equal in magnitude, because they are already opposite in direction. So your S is equal to RA times cos alpha. So put the value of RA, this RA, P over sin alpha here. So cos alpha over sin alpha is cotangent alpha, so P times cot alpha. You may not get this term in your scientific calculator. this button in your scientific calculator. So what you have to do, you press this function. There is a fraction function like this. Enter 1 here and enter a tan alpha here. So this becomes your cot alpha. So 1 over tan alpha, that is cot alpha. So that comes out to be 2.00087774. So P times that. So the axial force S developed in the tie bar is 2 times the load P that you are applying at the end B for the weightless bar AB to be in equilibrium, and the tensile force developed in the tie bar S is equal to 2 times P, is 2 times your applied load P.